Okay, so today's question has two parts and it can be found in my Google document, but I'll also read it out loud. So it says, a golf ball that has a diameter of 4.2 centimeters is launched 10 meters into the air, spinning at 5,000 RPM. The ball then lands on the green, leaving a divot 1 centimeter deep. For a brief moment, the ball spins inside the divot at 2,500 RPM before hopping out of the divot. Draw a graph that represents the ball flying in midair, as well as a graph that shows the ball's spin while stuck in the ground. And then label the domain and range for each graph. Okay, so first thing, I drew our golf ball here with a diameter of 4.2 centimeters, and then I also have the graph prepared, but we'll get to that in a bit. So let's write down what we're given. So we have an RPM of 5,000. Now, this is our period, but we need it in terms of like seconds per revolution. So that means for every 60 seconds, there's 5,000 revolutions. And so this gets us 0.012 seconds per revolution. Okay, and so now when we find our b value, it's our period equals 2 pi over b. So our period is 0.012 equals 2 pi over b. And so when we solve for b, we just switch these two. So we get b is equal to 2 pi over 0.012. Now, our a value will be 2.1 centimeters. That's our radius of our golf ball. Our d value is equal to 10 meters, or 1,000 centimeters. And we don't have a c value for this question or for this graph, because the question didn't specify where to start our graph. So we're going to use just sine for this one. So our c value is 0, basically. Now that we have that down, we can write our equations. So y equals a sine of b, and then x minus c plus d. So when we put in our values that we get y equals 2.1 sine, so our b again was 2 pi over 0.012, and now we just have x plus 1,000. Now, when we write our graph down, so I have time on the bottom here, and then we have our height in meters, and so our max height was 10 meters, or 1,000 centimeters, which is where the golf ball is spinning in midair. And so that's where the center of our our wave will be. And so the apex, which is 2.1 centimeters, is up right here, so just past the 1,002 centimeter mark. And so when we draw our graph, we're going to go up like this, down, and we're going to do two periods of oscillation, basically. So start right here, go up, back down, just past 998 meters, because the diameter is, because the apex is 2.1 centimeters. Then back up, and down again, And perfect. So that there is 2 full periods of it. And so now it asks for us to define the domain and range. So the domain, so the x, we have x is in between 0 and then 0.024. And then, of course, x is an element of the real numbers. And we said that x is between this because where we start a graph at 0, the origin here, or 0 on the x, and then we go to 0.24 seconds because we did 2 full rotations. And so our domain, we're just taking between those values. And so our range, we're going to do something similar. So y this time. And so we have y is between 997.9, right? Because this point is just below 998, just by 0.1. So y is right between that and less than 1002.1. And of course, y is an element of the real numbers. And that is the first part of the question. Now, for part 2, when it's asking about the ball that's stuck in the green, here I have drawn the ball. And so right here, this is 1 centimeter under. So this line here represents the ground. And so we know that this distance then, because, or I should say this one, is the radius, which is 2.1 centimeters. And so since this is also 2.1 centimeters, this little bit right here has got to be equal to 1.1 centimeters. Okay. Now, again, we can figure out what our max value is going to be and our minimum value, because this time is a bit trickier. So we have our max will be equal to the diameter, so 4.2 minus 1, because we're going down 1, which is equal to 3.2. So that means the max height up here will be, on the graph, will be 3.2. And then our minimum will just be -1, as you can see on the graph. Now, so our D value is going to be 1.1 centimeters, because if we take 0 as the center of the golf ball, we're actually going up 1.1 centimeters because it's stuck in the ground. Now, our A value, again, is going to be the same, 2.1. Our C value, again, is just going to be 0. And now our B value, so this is when we use the period again. So we have a period of, it's moving at 2,500 RPM. And so this is equal to, so 60 seconds divided by our RPM, so 2,500, which is equal to 0.024 seconds per revolution. And now to find our B value, again, we take this number, so 0.024 is equal to 2 pi over B. And so again, to find B, these two just switch, so B is equal to 2 pi over top of 0.024. Perfect. So now, again, we're able to start our graph. So why don't we use cosine this time? So y equals a cosine of b, and then x minus c plus d. So subbing in our values, we get y is equal to 2.1 cosine, so our b value, 2 pi over 0.0224, tearing the paper a bit, and then just our x, because we don't have a c value, and then plus our g value of 1.1. Perfect. Now we're able to start graphing. So now that we're using a cosine value, we're going to automatically start at our max value here at what we said was 3.2, and we're going to go down just like this through the center down toward our minimum value of -1, and then back up again toward the center. Now up to our max, that's 1 period there, and bang, we'll go back down through the center, down toward our minimum again, turn back around, go up, and that is our 2 periods of oscillation. So now that we have that, we can find our domain and range. So our domain, again, our x, we'll have x, and so our x value will again be between this point and this point, so 0. So x is greater or equal to 0, and then it's less than 0.048. And then, of course, x is an element of the real numbers. And then for our range, we're dealing with our y this time. So y, so this time y needs to be greater than or equal to -1, but it's less than 3.2. And then, of course, y is an element of the real numbers. And that is everything. That is the question. Make sure you like and subscribe, and maybe I'll see you in the next one. Thanks.